So the title of this video is not clickbait. We are going to actually implement the md5 algorithm in bash, or at least attempt to. We are going to do this in pure bash. What I mean by that is we are not going to fork any external utilities. So no like GNU utilities, no outside programs, nothing on our file system. We are going to use nothing but bash's built-in commands that it has. Why are we doing this? I don't know. It's going to be fun and it's going to be incredibly challenging, but hopefully it'll be entertaining. In my previous video, I talked about coproc in bash. It's a super fun keyword. Go check it out if you haven't already. But in that video, one of the uses of coproc was to fork out an external tool that calculated MD5 of the input that we gave it. But in that video, I think it was JavaScript. Now at the end of that video, I said, would you guys want to see me make a pure MD5 implementation? And a bunch of you said yes, so I got to give the people what they want. We're going to be doing that today. So if anyone's been watching for a while, I've talked about this before on this channel on my live streams. I like to do Advent of Code. It's a programming like puzzle challenge thing, super fun, ton of fun, and I like to do it all in pure bash, or as pure bash as I can get it. And for one of the challenges, I had to fork out to an external MD5 tool. I wasn't happy with that. Some people on my Discord weren't happy with that, and you know what? I agree. So today we're going to right that wrong. We're going to implement MD5 in bash. We're going to have some challenges, okay? I anticipate 3 big challenges with this, but we are going to do our best to get past them. First things first, bash is slow. It's just going to be slow. Even if it works, it's probably going to be slow. I don't know what that means. I think we're talking minutes instead of seconds, but we'll see when we get there. Processing null bytes or reading null bytes in bash is going to be difficult. It's not really even kind of possible, but it kind of is with a hack. We'll deal with that when we get to it. And the final challenge, I think, is just that this is going to be a math-heavy algorithm, and I'm not that good at math, okay? I'm decent at it, but we're going to have to do some bit shifting here, so I anticipate that I'm going to get some things backwards, and you guys are going to yell at me in the comments, and that's fine, but I am driven, I'm determined. At the end of this video, I really want to have a working MD5 implementation in bash. So yeah, I think with that, let's jump into it. So first things first, we are running here on my Mac. Yeah, I can type. What a good way to start the video off. So, okay, first things first, we are running on my Mac here. This should work on any operating system, Mac, FreeBSD, Illumos, Linux, because we're only going to use bash built-ins. So right now we're in my development directory. Let's go ahead and make dir bash MD5. I'll eventually put this code on GitHub. I'll link it below, assuming we can get it working. But yeah, so this all going to live here. We have nothing in this directory right now. It's completely empty. So before we get started, I kind of want to show you guys what the MD5 checksum looks like if you haven't seen it before. So you can echo like data. Let's say we have hello here. So if we echo hello, it prints hello to the screen. There's also a new line there. If we were to pipe it to a hex editor or a hex dump utility, you can see that the 0A byte is there. That's the new line, or like the line feed character. We can also pipe this to, I'm on my Mac, so I will have MD5, and that is the MD5 checksum. This is what we will be doing in bash. If you're not on Mac, you might not just have the MD5 tool, but you might have MD5 sum. So you can go ahead and run this. It puts a hyphen here because that's the name of the file. In this case, the file was standard in. If you don't have that, you'll probably have OpenSSL MD5, and there you go. You can see that the MD5 of standard in is this. They're all the same, B19, 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 I'm just looking at the first couple of characters. If you were to print nothing into it, so if we were to do a printf of absolutely nothing, we will get this D41D8. If you're like me, I've seen this, I recognize this. The MD5 of empty data of no input data is this. This is what it looks like. So when I see this string, that's usually an indication that like, oh, someone's trying to MD5 nothing. You can also echo -n, this, pipe it to like MD5. You'll get the exact same thing, D41, MD5 sum. Same exact thing. So at the end of this video, we should have a bash script called MD5 that when we run it, it will be able to take input from either standard in or the name of a file, and it will write this data to the screen. I'm thinking we'll keep it simple. We'll have it just output the MD5. I'm not going to put the name of the file or anything like that. I'm not going to try and match it. I don't even think I'm going to take multiple files here. I think just a simple goal will be for our script, which doesn't exist. I'm just hallucinating this. We should be able to MD5 file dot whatever, or we should be able to read that in from standard in. So this should both work once it actually gets working. I guess I could create the file, couldn't I? Echo hello, write that into hello.txt, and then we can MD5 hello.txt. And there you go. You can see that. You can also do MD5 sum, hello.txt. Of course, it's all going to work. They all pretty much have the same usage. So we're going to do things a little bit different on this channel right now. If you've watched my previous content, you know that I kind of just dive into it. We're going to use a fun little thing called test-driven development. That's right. We're going to do some TDD here. I'm going to write the test first, and then we're going to write the code that will make the test pass. So let's envision what some tests for this would look like. We have hello.txt here. Let's go ahead and move those into a directory called files. So let's move hello.txt into files. Now if we ls, here is what we have. So let's go ahead. We have hello.txt. We should touch empty.txt. This will be an empty file. And then we can make a kind of a large file. This will be a large binary file because this is important. I want to be able to read binary data. I want to be able to MD5 JPEGs. I want to be able to MD5 executables. I want to be able to MD5 anything, not just plain text files. So let's go ahead and create a file. We can use DD to do this. Our input will be dev urandom. Our output will be, let's just say random underscore 4 kilobytes dot bin. It's just going to be a 4 kilobyte file dot bin because it's going to be random data. So that means we need a byte size of, let's just say, I don't know, 1K and a count of 4. So if we do this, there we go. Now if we ls-lh, you can see that we have empty.txt, which is 0 bytes. That's great. We have hello.txt, which is 6 bytes because hello is 5 characters plus the new line. And then we have random 4 kilobyte, binary data, which is 4K. So perfect. That's awesome. Here's what we can do. You ready for my test? For my test, where are we? Are we in the files directory? We are. I don't want to be there. Okay. For this test, I want to be able to MD5 file star. And here we go. Here's the MD5 of all those files. I want the test to go through and verify that our script that we're going to write creates these MD5. So let's go ahead and write that to a new file. We'll call that test MD5. And we'll go ahead and turn this into a bash script. Here's what we're going to do. Put the shebang up here, user bin, env bash. So it looks like a bash script. It's not really. You wouldn't want to execute this. chmod +x test md5. Let's go ahead and pull it back up. And let's do some cleanup here. We're going to make an associative array where it'll be file name as the key and checksum as the value. So let's declare -a for an associative array. We'll call this files equals, we'll open the array, and then we'll close the array, and then we'll just do some cleanup here. So we can get rid of this. We can replace the open parens with open square brackets. We can replace the closing parens with closing square brackets. We can get rid of all the white space. And that actually is valid. Believe it or not, this is totally valid. I do like putting quotes around here just so we know that they're strings, but technically speaking, you don't need them. That would have been just totally valid as is. So we have this where we have 3 elements in this array. So now we can just loop over this array and make sure it makes sense. So we can do a for file in files. We put the exclamation mark because we want to loop over the keys, not the values of the array. Do done. And now we can grab the value out of the array. We're going to call the value, this is going to be a little bit confusing. We're going to call it want because that is the value that we want. I know that might be a little bit confusing, but the value that we want is this. And then we're going to have another value called have. So what we have versus what we want. And in order to get have, we're going to call the MD5 program that's in our current directory. It doesn't exist yet. I'm hallucinating it. We're going to create this on file. And then we will make sure that want equal have. So then we know that the output of the command matches the checksum that we have on file for it, if that makes sense. So over here, we can echo okay, else we can echo fail. We have, and then we'll put what we actually got from the user. Now we need to actually return an exit code that makes sense here. So what I'm going to do is I'll say that we'll assume success. If we have a failure, then we'll go ahead and set the code equal to 1. And then down here, we can exit that code. So then we'll know if there was a failure based on the exit code here. We should also probably print the name of the file. So we can do something like this. Checking file is want ... space. There we go. So I'll show you what this does. So if we look at the source code here, so you can see what we have for the source code, we can run test md5. It's going to fail. We don't even have the md5 script in our program or in our current working directory. We haven't created it yet. So this is going to fail. But look at this. As you can see, we get checking files hello.txt is B1946AC. Fail. We have an empty string. And of course, we have these errors because that script doesn't exist. So let's go ahead and create that script. Here we go. This will be our implementation of the MD5 algorithm, which I haven't even shown you guys yet, but don't worry, we're not even close to being able to implement this yet. Let's make it executable, and let's go ahead and have it print echo checksum here, LOL. So it doesn't work if we run MD5 on, let's say, files hello.txt. Hey, that's cool. If we give it a standard in, hey, that's cool. It's wrong, but it's cool. So if we run the test, take a look at this. We're checking to see if the file is this. Fail. We have checksum here, LOL. Fail. We have checksum here, LOL. Fail. We have checksum here, LOL. So all we have to do is implement this script to output the right checksum for those files, and we are good to go. That means our implementation is working. So hopefully it's not too bad. So I'm going to tackle what I think is going to be the most annoying part of this video. it's not actually even generating the MD5, at least I don't think it will be. I think it's going to be reading the data because we have to read data from a file that could potentially contain null bytes, and Bash is really bad at reading null bytes. Or put differently, Bash is really bad at storing null bytes. You can't store null bytes in a string. So let me show you what I mean by that. Let me show you what that looks like in practice. If we were to printf hello space world, it'll write to the screen like that. There's no new lines, so that's why the prompt appears there. Printf is super nice because it takes a -v argument. I can put a variable name here. So I could say foo. And now if I echo $foo, take a look at that. Hello world is whatever was output from printf here. That's super cool. If I were to put a new line here, this is going to blow your minds, but look at that. Hello world has the new line in it because printf turned this into a new line before storing in the variable. That's super good. What if we had a null byte here? Hello null byte world. Look at this. We only get hello. If we were to pipe this to a hex dump, you can see that we don't have that null byte. We have the 0A because echo is appending a new line, but we don't have the null byte. Bash just terminates the string because it sees the null byte. So we can't store null bytes in a string. We're going to need a different data structure to this, but this causes problems when we go to read data. So let's get our program reading data first. Once we have that working, then we can start processing the data. So what I envision we're going to do is we're going to read the data byte by byte. We're going to turn that byte into a number, so between 0 and 255, and we're going to store it in an array. That way we can deal with it, but we'll get to that when we get to that. Let's modify our md5 script to take data from standard in. We'll just worry about standard in for now. We'll worry about reading from a file later. We can do the really classic while read -r line do done echo line. This is a very simple script. It's a while loop that calls read. Read uses \r, which is a super simple option to not mangle any sort of input. It doesn't do any / processing. So it'll give it to you. You can think of it as like raw. It's like raw input. And we're going to save that as the variable line, and then we're going to echo line. So this is a super simple program that just takes its input. So let's say we cat files hello.txt. We pipe it to our md5 program. We just get the same exact output, right? So let's test this out. Let's show what it does. If we were to echo hello space world, pipe it to md5, hey, it works. The loop only ran once. The loop I'm talking about is inside the md5 script. It only ran once because there was only one line to read, which is super simple. We could interpret new lines here, so we could put a new line here, hello world, foo, bar, baz, and then we get all of these as separate lines. That's super cool. That's super awesome. There are some issues with this though. You ready for this? What if we had space, hi, space. And then we run that, look at that. We've lost the spaces to the left and we've lost the spaces to the right. That's not great, that's not fantastic. The reason that happened is because the read command in Bash will try to do processing around spaces, white space by default. And what it's actually doing is it's not technically white space it's looking at. I mean, it is looking at white space, but we can control that programmatically with the ifs variable. So let's set this to nothing. This tells the read command to not do any sort of processing or splitting of the data that's reading it. It's just going to give it to us without doing any sort of special treatment to it. So if we rerun this, we run this, look at that. We have our leading spaces here and we have our trailing spaces here. I know it's hard to see, but the fact that I can highlight these tells you that they're there before we get to the end of the line. So that's the first thing we have to do. We have to add that stupid little IFS line. Not a big deal. But the next problem is, of course, what I talked about before, null bytes. So let's go ahead and put those in. If we printf hello, null byte, world, new line, and then we print that, look at that. We get hello, world, but there's nothing in between it. So you might think like, oh, well, the null byte's there. It's just not displayed. Pipe it to XXD, and you can see that there's nothing between the O and W in world. That null byte is just completely lost here. This is not what we want. This is not great. We are just completely losing that when we read that in. But again, don't worry. I have infinite tricks up my sleeve. Okay, you ready for this? If we do help on read, which gives us every option for read, we were using read-r, do not allow backslashes to escape any characters. Hey, that's awesome. Check it out. -d, delim. Continue until the first character of delim is read, rather than new line. So read, you know how we're doing read in a loop here, where we're doing while read line? This is looping over new lines. We are reading lines. Well, how about instead of lines, why don't we just read a chunk of data? So I'm just going to, that's not right. Chunk and chunk. There we go. We're going to read a chunk of data and we're going to give it a different delimiter. What delimiter are we going to give it? Nothing, because this will get processed like a null byte. This will get processed as though it were a null byte here. So let's go ahead and do this now. we can do a printf foo null byte bar null byte baz null byte, pipe that into md5, and look at this. We got foo bar baz. So I'll pull up the source code just so you can see what's going on here. Each chunk is each section separated by the null bytes. So once we've moved on to the next iteration of a loop, we know that we've skipped over a null byte, which is pretty cool. The nice thing is it also ignores new lines. So if we had F, O, O with new lines around it, the new lines are retained. I guess this is a bad example because the new lines show up exactly the same. Hold on. Ready for this? Let me make this easier to see. Let's echo greater than, less than chunk, and I'll pull up the source code so you guys can see. So this is what we're going to print. We're going to see how many times the read command ran. Look at this. The read command ran 3 times. So we had this chunk of data, which has new lines in it, but it was read through one invocation of read, this chunk of data, and this chunk of data. So we are successfully chunking the data on new lines. So that's great. This is huge. Is there another problem with this? Absolutely. What if that null byte were gone? In fact, I don't even like these new lines here, so let's get rid of these two just because they're kind of annoying. If that null byte is gone, notice that we have foo and we have bar, but what happened to baz? Well, let's go back to our source code and figure out what's happening. This while loop is looking at the output of this command, not the output, sorry, the exit code of this command. So if it's successful, it will iterate again. If it's a failure code, then it will stop iteration. So once we get down here, loop has ended. Let's go ahead and just output this so we can see what's going on here. And let's go ahead and say echo, this was left over $chunk. So when we get to the end of the loop, we'll print what was left over. So when we run this, we can see that we have foo, we have bar, the loop has ended, and this was left over baz. So we didn't actually hit the delimiter. The read command failed, but the data was still loaded into the variable for us. By contrast, if we had the ending null byte here, we would see that the loop is ended and this was left over. We had nothing left over. So there's a couple ways we can accomplish this, but we have to kind of deal with this. You see how annoying and tedious this is going to become? I mean, it already has become annoying and tedious, but this is not a big deal. We can work through this. We can make this work. There are a couple ways to approach this. I'm going to do it the way I like because it's my code and you're watching my channel. So what I do when I'm figuring out loops like this is I just make an infinite while loop, and then I put this as a command, and then I figure out my own stopping condition, if that makes sense. So we have an infinite loop here, process, input. We read the data into the chunk variable, and now we're gonna have an exit code. So we can tell if the read command was successful or not. And this is very important because normally, if it were unsuccessful, it would have stopped right there. But instead of stopping there, we could stop at the bottom. We could check if code not equals 0, that means the read command failed. Then we can break out of the loop here. So read failed, so we are done processing. But notice what we're doing here. We're not breaking the loop immediately when the read fails. Even if the read fails or it's successful, we still print the chunk here. So this is the secret. This is the key to it. So let's go ahead. Let's get rid of this down here and let's check our work. So if we pull up the source code, you can see it there. Let's go ahead and run this. Foo, bar, baz, and then nothing here. And then if we do this, we have foo, bar, baz. So this one works, but this one doesn't quite work. Now here's the thing for our code though. This doesn't matter. Now I know it's printing the screen and it's ugly. Look at this. There's nothing between this. That's because there was a null byte here and we're saying what came after this null byte was nothing. But in our code, this will be okay. Because there's nothing there, there's nothing to process. If we envision a function later down the road that will take a list of bytes to process, like it'll process FOO, it'll process BAR, it'll process BAZ, we're going to tell it, hey, process all the stuff between this less than and greater than. There's going to be nothing. We're going to be okay. So even though it looks gnarly here, this is not actually going to be a problem, which is good because hopefully you guys already see how annoying this is becoming. All right, let's do some more work here because there is another problem with this. We're calling read and our delimiter is the null byte. What if that file doesn't have a null byte? What if it's a very large file without a null byte? Can you think of one? Well, I have user share dict words on my machine. This is a word list. This is a word list with 235,000 lines. It is 4 bytes because it's a symlink. Okay, let's actually get the real file. It is 2.4 megabytes of data. Now that's not huge, but it's not nothing. The reason I bring that up is because instead of calling, let's say, printf all this stuff, let's go ahead and clear the screen and let's cat user share dict words into this program. Notice that it's hanging. Notice that we have this here. And then if we go all the way to the top, we have this here. We read everything as one chunk. There's one variable which stores all of this data in it. Do you see why that's a problem? Because null bytes are our delimiter, if the file is really big without ever experiencing a null byte, we're going to attempt to load the whole thing into RAM. That's not good. So what we need is a second check. So yes, we're using null byte as a delimiter. That's our only way of being able to detect null bytes, but we need a second stopping condition. We need to stop if we see a null byte or if we've also read a certain amount of data. So luckily read has this -n argument. Return after reading n chars characters rather than waiting for a new line, in this case the null byte because we're changing it, but honor a delimiter if fewer than n chars characters are read before the delimiter. That means we can do something like this. We can read this with a -n of, let's say, 4096. Arbitrary, you kind of see this a lot in code. We're going to read 4 kilobytes of data or up until a null byte, whichever comes first. This is really cool. This is huge because we still have the exit code here, and then we can actually get the length of data we read. So we could say n equals the length of chunk as a string. So now we know how many bytes of data we've read until we hit either a null byte or we hit the 4096 limit here. So we could do something like this. We could just print read n bytes. There you go. And then once the code is a failure, then we can break. That's super cool. So let's go ahead and rerun this now. Look at that. Do you see what happens here? We read 4096 bytes a lot. I'm scrolling. And then if we get to the bottom, 3517 was left over. That is huge. That is awesome. So if we were to printf hello null byte world and run that to md5, look at that. We've read 5 bytes and we've read 5 bytes. Now we stopped at the null byte. We haven't detected technically if we've hit a null byte or we've hit the 4096 limit. This is important because if we hit a null byte, we have to manually insert that ourselves. So let's go ahead and add that logic now. We need to figure out what happens when we've read that amount of bytes. So let's do this. We can also put the code here. So this was the exit code of read. I don't know why it indented like that. Let's rerun the user share dict words in md5, and we can see, look at this. We were able to read this many bytes. It's less than we requested, and now we have a failure code here. So this is huge. This is great. This is awesome to know. So let's just stub out some code, process the data here. This will just be a to-do message to us to process the data here. Once we're done processing data, then we'll check, did the read command fail? If the read command failed, then we know that we are done processing data. Yes, we are conflating other possible errors, but we can deal with that later. And then below this, we can say if n is less than 4096, which was the value that we used above. If n is less than 4096, then echo we encountered a null byte. So we know we've encountered a null byte if we were able to read successfully less than 4096. So this is huge. This is very important. So if we run this again, we can see that there are no null bytes in this file. That makes perfect sense. That's awesome. If we were to run this, we can see that we read 5 bytes. Hello. We encountered a null byte here, and then we read 5 more bytes. So let's try and break this a little bit. We could just do like this, 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 and we can see that, look at this. We read 0 bytes. We successfully read 0 bytes. That's good. So we didn't stop processing. So we read 5 bytes, hit a null byte, read 5 bytes, null byte, null byte, null byte. So 5 null byte, 5 null, null, null. This lines up. This is working. This is exactly what we're seeing. This is huge. We are making good progress here. Told you there'd be a lot of setup just to read the data. So is this working 100%? No, there are still more issues. You ready for this? Let's have some fun here. Echo minus n. So that is no data at all. If I echo minus n, literally nothing will get printed to the screen. Another way of doing this is you could just printf like this. But let's do echo minus n, and let's pipe this into md5. Read 0 bytes, code equals 1. So we've read 0 bytes. That's great. Let's go ahead and add a new byte to this. You ready? I don't think it's going to show up on the recording until I click the button, but take a look at this. Let's go ahead and put an emoji into the script. Read 1 bytes. So the emoji has a length of 1. Do you know how many bytes are actually in an emoji? Well, this one specifically, let's take a look. 5. There are 5 bytes in this emoji, but Bash thinks it's 1. So this is a locale issue. Bash is treating these like strings because that's what we're saving it as. And that's fine until we want to process data that isn't strings. So in order to do this, there's actually a super simple fix for this, is that we can change our locale. LC, locale, underbar all equals C. So we are changing it to the C locale. We're not doing any sort of like UTF-8 stuff on this. We are just treating one character as 1 byte. That's what's going to change here. There may be some downstream effects of doing this. We can worry about that later. But take a look at this now. Now we have read 4 bytes. Is 4 bytes correct? Didn't I say there's 5? Oh my God, there's 4 here. Okay, wow, my eyes must just be getting old. I said there were 5. There are definitely 4 here. Yeah, I don't know why I just didn't look at this grouping. It was something about this color that's just really hard to see. You know what? It's past midnight here. I'm gonna go put my glasses on. I think that'll fix it. My contacts, I think, are getting dry. Okay, wow, yeah, that is so much clearer to see. It's still a little weird. It might just be the 4 dots next to each other. Whatever, that's fine. Everything's working. So let's recap what we have right now. We are able to, with all of this code, read data from the file system, and we don't do anything with the data. Here's where that processing will go. We're able to read information from its input. We're able to read it in chunks, so it's fairly efficient as opposed to reading 1 byte at a time, which can be kind of annoying. We can get the length of the chunk. We can figure out how much we've read. We can correctly handle null bytes, and we can correctly handle checking if the read was successful and there's still more to read, or if we are done reading. Yes, we are conflating errors. If read gives us errors other than it has encountered the EOF, we don't really detect that here, but I'm not worried about this. This is just for a proof of concept. Let's get this thing working before we make it pretty, okay? Okay, I just said we're gonna get it working before we get it pretty, but let's go ahead and pretty this up a little bit because this is where we're gonna be working out of. So right now, our script is super simple. It's called md5, and all it actually does is read data, and it doesn't actually do any md5 stuff. So let's go ahead and clean this up. The way I like to do that is I like to make a main method, and then we'll call main down here with any arguments the user gives us. We'll worry about those later. But our main method, let's go ahead and envision what our main method should do. We should take arguments from the user, a single argument, which is the name of a file. This is optional, but if they give us the name of the file, we'll process that. Otherwise, we will process standard in. Now, we can say if they gave us a file, then we can process the input. I'm hallucinating, this function does not exist yet. We can process the input from the file. Otherwise, we can process the input and we won't give it anything, and this will just default to standard in. So that's how I'm envisioning it. There are some other things we can do. I know some people will probably want to comment this. I could do this. I could say, hey, set file to $1, and if it's unset, use dev standard in. This totally works, and then you could completely get rid of this whole if statement nonsense. I don't love it because it does rely on your system having dev standard in. Every system I've encountered does have this like pseudo file existing for you, but I just prefer to leave that off myself, and then we can have a very simple if statement that will end up in the same function eventually, but you can see kind of very clearly what's going on here. In fact, let's go ahead and do this. Reading data from file, and then echo reading data from standard in. So we can clean this up later. Obviously, we can't print all this stuff to the screen or else our test will fail, but we'll worry about that when we get to it. I said we'll worry that when we get to it. We just got to it because I've decided that we should actually deal with that right now. What do you guys think? Let's make a debug function. I like this. We're going to make a very simple debug function, and all debug is going to do is it's going to check to see if some all caps variable named debug is set. We can pass this as an environment variable. If that's set, then we will echo debug, and then whatever the user gives us to standard error, so it won't clog up the output that we normally see, and then close it here, and then we can just return success. Nothing's checking the exit code here, but it's just good practice to make our function return success regardless of the state of the if condition above it. So we can change this echo to debug, and we can change this echo to debug. So hopefully this makes sense. Now we do call process input here. So let's go ahead and take this stuff that we have, that we've called process input here, and let's just turn it into a function. Process input like this. Let's go ahead and take all this, move it up a level of indentation, close this, and now we should be good. And the way we're good is for all the variables that we've created here, we should call them local. So we have local n, local this, local chunk. If we want to optimize it, we could move this outside of the loop, technically, I guess. I don't want to get caught up prematurely optimizing. Let's make this a debug call, and let's make this a debug call. There we go. Cool. So now if we rerun our script, we should be able to say md5 and let's read it in from files hello.txt. And it prints nothing to screen because we don't have the debug enabled. So let's go ahead and enable the debug. Debug equals 1, md5, that file passed over standard in, reading data from standard in, read 6 bytes, code equal 1. That's great. That's huge. So now if we get rid of this redirection and we just pass it as an argument, read data from files hello.txt, read 6 bytes. Look at that. That is huge. We were able to successfully read files. That is cool. What if we put the ultimate test here, the random 4 kilobyte binary file thing? What's going to happen here? I anticipate we're going to get a lot of data. Okay, that was way faster than I thought it would be. So I bet if we were to take all these numbers and add them up, that we would encounter 4 kilobytes, or maybe 4 kilobyte less each time we encounter a null byte. We'll have to figure that out because we might have to store the total byte count of the file as we read through it. So this is huge. This seems like this is working. This is super awesome, actually. Yeah, what was I so afraid of? I mean, I'm the guy who wrote an HTTP web server in pure bash with no external utilities. It's a really fun video. Go check it out if you haven't watched it. It's super cool. I love doing these pure bash videos. Let me know in the comments what you guys think. Do you guys like these videos? Obviously, we still have so much more to go, but like I just figured I would check in with you guys. Let me know if you guys are enjoying this, if you love these deep dives, how you feel about them, what kind of content you guys want me to make. If you made it this far, obviously, hit the subscribe button. Let's go ahead and get that number very big. I'm at 108,000 subscribers at the time of this recording. Yeah, let's just jump back into it. I'm not going to waste your time. So here's what we need to do. Right now, we have to process the data here. So we have a chunk of data, but we don't want to process the data in chunks. We want to process it byte by byte. So we have our process input here. We're going to want a process byte function that will take a byte as the first argument and then do something with it. What's it going to do with it? I have no idea. For now, we're just going to debug process byte. That's all we're going to do. We're just going to print to the screen. That's what we're going to do here. So now we have to loop over the data in the chunk and process it byte by byte. Now this is actually surprisingly easier than you think it would be. We just have to do a simple for I equals 0, I less than n, which is the amount of bytes that we have read, I plus plus. Now we can get that character out. So C will be the character here, and we will extract that from chunk, substring starting at I, going for 1 character. So remember, chunk is kind of like a string, so we can substring into it starting at position I, only getting 1 character. So we're basically just indexing into it, but we can't index using the array notation. So let's go ahead and call process byte on C. And then there we go. Loop the chunk and process byte by byte. So there you go. That's pretty simple. We could also go ahead and we have local chunk here. We can also add I and C because we have those in the loop. And then I think here's the thing. When we encounter a null byte, we have to add that back in because the null byte's not part of the string, so it's not in the chunk. So when we encounter a null, we have to also call process byte on a null byte. We'll have to somehow give it null goes here. We'll have to figure out how to pass that in. But until now, we're just going to do this as is. So let's go ahead and rerun this. I don't think we want to do the random 4 kilobyte file because that's going to be huge. So let's run on hello.txt. So look at this, process byte on HELLO. And then look, the new line even shows up here. That's great. So we are looping over it 1 by 1. This is going to be a mess if we start doing it on the random kilobyte file. And the reason why is because these are the actual ASCII characters themselves. We don't want that. We want the number. We want to convert ASCII to the number. Now that might be confusing what I'm saying here. We don't want to just printf H. We want to printf what H looks like when it is turned into a number. And we can do that with printf. Printf supports %d for a number, and then we can give it the character we want to convert. And the way you do that is super weird. If I just give it H, it yells at me because it'll say H is an invalid number. But if I put a single quote in front of H, really look at this. It's super weird. I have double quotes around the whole thing and a single quote in front of H. Suddenly, I get the ASCII representation of H. How crazy is that? I can put I, which should be the next one, 105. I could put J, which is the next one, 106. Capital J, 74. Capital K, 75. You can convert a character into its number using this notation with printf. So this is what we're going to do. So when we process the byte here, we're actually going to turn it into a number first. Printf minus v means save it into the C character. We're going to overwrite C here, and we're going to give it a %d as the format specifier, and the argument will be double quote, single quote, $C, double quote. Really weird to look at, but we are turning it into the number. That way, if we turn it into the number, this can just be a 0, because that is the number of the null byte. So super weird, super confusing if you've never seen this syntax before. But take a look at this. HELLO, new line. ASCII 10 is new line. You could prove that by just, catting files, hello, piping it into XXD, and we can see that we have 68 hex. 68 hex should be 104 decimal. I could prove that. Let's just fire up JavaScript, right? OX 104. Nope, I did it backwards. Hold on. I told you I'm bad at math, okay? I told you I'm bad at this. 68 is H. OX 68 becomes 104. So 68 in hex becomes 104 in decimal. 68 for H becomes 104. That's what's going on here. 0A, I recognize that as the line feed because that is 10. If I put 0A here, look at that, it becomes 10. That's what's going on here. So if all that is good, then we should be able to give our MD5 program the random 4 kilobyte bin file. There's gonna be a lot here. Actually, it's gonna be nothing if I don't put debug. So, wow, that's so much faster than I thought it would be. This might not be slow, guys. When this works, this might not actually be slow. So we are able to process the file. And when you see, oh, we read 1 byte. Okay, here's the byte we read, and then here's that null byte we interjected. We read 165 bytes. There'll be 165 lines until we interject our own null byte. And then we don't put the null byte at the end because we had the code equals 1. This is coming together better than I thought. Of course, we haven't done any MD5 algorithm stuff yet, so we'll see what it looks like when we get there. We're still just trying to read the data. So let's figure out how the MD5 algorithm works, all right? I got 2 pages pulled up. Here is the actual RFC for MD5 here. You can see it's RFC 1321. You can look this up. I'll have all this linked below, of course. And there's a lot of good information on how it works. There is a lot of stuff like this where I'm like, oh boy, this is overwhelming. And then there are actually some code examples here, which are super good. I looked over this a little bit just to make sure I'd be comfortable enough doing this in the video. And yes, I am, but there's a lot going on here. I actually kind of like the way the Wikipedia article lays it out better with some asterisks because there's still some weirdness here. But the nice thing is they give you a pseudo code version of it, which is nice. You get all variables are unsigned 32-bit and wrap module 232. This is going to be super nice because we can just logically add it against, U32 max, and this is going to be fine. Bash can do this all day. We have an S variable that just has these pre-computed values. And then we have this right here where we have to, from 0 to 63, read it into this variable K by doing this calculation. Luckily, they pre-computed this all for us, so we can just store these as constants. And then we have these 4 variables. So at the heart of it, MD5 takes these 4 32-bit numbers and then appends them together to create a 128-bit message, and that's the final output of MD5. So you start with these variables, they're constant, they're just set to this, and these variables will get modified as we churn through the data. So it's a little bit out of order here. When they use the word message, they mean our input. So they're saying, okay, take all of your input, then add a single bit, and then keep of 1, and then keep adding the bit 0 until the message length in bits is 448 modded by 512. It's all in bits. This is super annoying because we're working in bytes, but luckily we're not alone. Look at this notice right here. The 2 padding steps above are implemented in a simpler way in implementations that only work with complete bytes, which is going to be us. So instead of having to add a single bit, we can just append 0x80, which is 1 and then 7 zeros following it. So we can append this number and pad with 0 bytes so that the message length is 56 mod 64. This is going to be so much easier. Don't worry, I'm going to go through all this. I know I'm going through this really quickly. And then we have to add the original length in bits, mod 264 to the message. So we will need the length of the entire file. That's important. So we're going to go through every time we process bytes, we're going to count how many bytes we've processed. Very simple. We're going to use global variables for this. For each 512-bit chunk of padded message, 512 bits, super annoying. That's just 64 bytes. 512 divided by 8 is 64. We just have to process 64 bytes of the message. So really look at this. this is the entire algorithm. The whole algorithm is just looping over 64 bytes of messages. So we have the original message, then the padding of the ones and the zeros, then the padding of the length of the file. So it's actually really simple. We just loop over 64 bytes of the data. We set these local variables equal to whatever these global variables were set to. Remember, these were given to us from on high. We do all this calculation. We'll worry about that later. And then we just update these 4 variables. And then at the end, those 4 variables are our answer. This means that we don't have to store all the data in memory. We only have to store at most 64 bytes of data in memory. This is super useful. We can just use an array, store 64. Once we hit a length of 64, process it, run this whole thing, and then we've updated our global variables, and then we'll go through and keep storing up data until we hit 64. This is going to be super simple. Let me instantly rephrase that. This is not going to be super simple. I'm sorry, that's not what I meant. This is going to be straightforward. It's not going to be simple. This is like when you're at the gym and someone says, hey man, what's the difference between benching 1 plate and benching 2 plates? Like benching 1 plate, 135 pounds versus benching 2 plates, 225 pounds. There's a big difference, but benching 2 plates is just as simple as benching 1 plate. It's really easy to explain to someone. Yeah, you hold the weight here and then you push it up and you bring it down. It's very simple. It's very straightforward, but not actually simple. It's very difficult because gravity's pulling on them differently, but the motions are the same. So I think I should say this is going to be straightforward. It's not going to be simple, but it's going to be straightforward. So we're basically just going to copy and paste this into our code, and we're just going to implement it. And we're going to, my God, cross our fingers, because I am probably going to make mistakes here. That's what I think our biggest issue is going to be, that I'm just bad at math and I'll probably make mistakes. Like I said before, we are going to have to store up to 64 bytes of data before we process it. I'm going to call those blocks. I don't know if this is the same terminology that they use on like the article here, but we're going to say block equals empty array. And this is going to store bytes until we hit 64 bytes. And then we're also going to take the global byte count. This is how many bytes we have read, and we're going to start at 0. Again, like I said, we're using global variables here because they're fast and we don't have to worry about them. Every time we process a byte, we should do a couple things. We should say byte count plus plus, because we've processed 1 byte. We should increment the byte count. Then we should store that byte in the block. So we can do a plus equal notation on this, and this will append it to the array. So now the array has grown by 1. Now we can check if the length of the array, this is the notation for doing length of an array in bash. If the length of the array equal 64, then I have some stray spaces here. Then we have a full block ready for processing. There we go. And then we'll close this if statement here. So if we make it down here, then we have a full block ready for processing. We can call process block. We haven't written this yet. We're just hallucinating functions again. We can call process block. And then once we've processed it, we can wipe out the block. We've handled those 64 bytes. We can bring everything back to 0. So hopefully that makes sense. Keep track of how large the input is. Store the byte. And then check if we have a full block ready for processing. Then we will call process block if we do. So let's go ahead and implement process block. Now process block is going to be literally this. Like, this is what process block is going to be. Before we do that, we are going to need some global variables. So let's go ahead and use these, and we will store them with the exact same names that they're using. I don't know why they decided to use lowercase s as an array of size 64 and uppercase k as an array of size 64. I don't know, but we're going to use these names because it'll make our lives easier. I'm just copying these off the Wikipedia article, and we are going to make them work for what we have. So we can say s equals, we'll open the array, move this over. Let's go ahead and get rid of some of these, get rid of those, close the array. And now all we have to do is get rid of the commas. There we go. And this might look weird, but this is just an array. So array spot 0 is here. Array spot 1 is this. Array spot 2 is this. Array spot 3 is this. You just separate elements in an array in bash by spaces. So you can actually kind of space things out like here. Kind of looks like a calendar, doesn't it? Like the output of the cal command. Do I have the cal command? Oh, look, you guys can see when I recorded this. Okay, I guess I do have the cal command. That's awesome. So the other thing I'm going to pull in is the pre-computed k table. just so you guys can see what I'm doing. Here's what I'm pulling in. I'm just going to take this and we are just going to paste it in here. So same deal. We will say K equals, open the parentheses here. Let's go ahead and wipe these out. Let's move them over a little bit. Let's close the parentheses here. So I would normally edit some of this stuff out, but I think you guys actually like seeing the Vim foo and stuff. I've also been thinking about getting a like an input display up here where I'm pointing. So like actually having my keyboard, what I'm hitting on the keyboard show up there. Let me know. That might be a little bit too distracting, but I know when people see me doing the Vim stuff, you guys kind of want to see what I'm doing and kind of see like what's going on. So yeah, let me know how you guys feel about this. This looks gnarly, but this is all valid. I promise you it's valid. Let's go ahead and run true here just because. Okay, let me back up and tell you what I did. Functions in Bash need to have some sort of body. So if you're in Python, you would have, that's not what I want. You would have pass here. So I just throw true here. The reason I'm doing that is to make it syntactically correct, because we can run it through bash -n to syntax check to see if it was wrong. Because it printed nothing, then we know that it is syntactically correct. We should also do this. I keep saying I'm going to become better at doing it, and I just don't do it. We should run shell check. We should probably try to make this code shell check clean. So cool. Actually, wow. This is really great considering what we've written so far. The only thing it's yelling at me about is that we haven't used S and we haven't used K. That's great. We haven't used them yet. We're just implementing them. So I'm actually really happy that things are working out like this. This is great. So again, some more data to copy in. We will need A0 through D0, and these will just be updated as the script goes on. So let's go ahead and copy this over here. We can just clear out some of this. We can clear out this, and we can clear out this. I don't know why there's comments over here. Let's go ahead and wipe those out. So there we go. We have the starting variables for this. Here's the beautiful thing about Bash. These are stored as a string, but we will coerce them to numbers. So even though it looks gnarly, here, take a look at this. We have A0 here. If we echo A0, nope, I have to put the 0 here. A0, it looks like this. But if we treat it like a number, like we just put arithmetic expression, we don't do anything. We don't plus or minus anything to it. We get the number from it. So this is super useful. We don't actually have to do anything to these numbers. Bash can just store these just fine. Once we start processing, they'll be stored like a number and not in this hex notation, but who cares? We're not looking at the data. We're not going to inspect it until it comes time to print it. Then we're going to have to return it back into hex. So yeah, this can be confusing for a lot of people. It's even confusing for me too, where the way Bash stores things is a string representation, and then when we treat it like a number, has to coerce it into a number, do some work, and then it kind of stores it back as a number. When I say stored as a number, it's a decimal string representation of the number, because internally computers don't have hex numbers, binary numbers. They just have numbers. When it comes to binary, hex, decimal, we're the ones who choose to display it like that. I guess there's an argument you could be made for saying it does store it as binary, but then we're talking about like hardware specifics. Let's not let this get away from me. Let's keep going here. We have a lot of good work to do. We have our work cut out for us here. So let's go over here. And let's figure out what we want to do. Now, we have to append some stuff to our input. So we have to, append 1 to the input. We have to append 0 to the input. We have to append the original length to the input. And then we have to process those bytes. Let's worry about that later. Even though they have it at the beginning here, we're going to worry about it later. We're going to start with this loop. And we're going to implement this loop because this is the loop that runs when it comes time to process a block. And we've already stubbed out our process block function. So let's go ahead and do that. So here we have process block. And I've just pasted it in here. This is not valid bash, obviously. Grok, turn this into valid bash. But don't worry, I'm your Grok today. I'm going to be the one turning this into bash. For each 512-bit chunk of padded message, so that means for each 64-byte chunk of padded message, that means we don't have the loop here. The loop is actually happening outside of process block. So we can get rid of that. If you're confused what I mean by that, where we call process block down here, we've already done that, looping over 64 bytes, so we don't have to do that again. Wow, this script is not happy with me. Break chunk into 16 32-bit words, where it's going to call it MJ, where J is between 0 and 15. So we're going to make an array called M, and it's going to take the chunk that we have, the 64 bytes, and turn it into 16 32-bit words. So we're going to have 16 elements of the array, and each element of the array will have 4-byte numbers or 32-bit numbers, because remember, everything operates on 32-bit numbers. That's what they promised us with the implementation of md5 on Wikipedia. So let's start doing some work here. In order to break the chunk into 16 words here, we're gonna need a loop. We're gonna do for I equals 0, I less than 16, because that is exactly what it says. You know what? Actually, let's do this. Kind of like the idea of keeping it as comments, because then it's kind of useful. We can kind of understand like a little bit what we're doing. We are going to break it into 32-bit words. Another way of saying 32 bits is 4 bytes. So we need to get the block at spot 0, 1, 2, 3. And then we need to get the block at spot 4, 5, 6, 7. Yeah, like I said, I'm bad at math. This is going to cause a problem. I think we need a second counter here. So we have I, we have j. J should be equal to I times 4. So j is our starting offset into our chunk. And then we also need that array that it defined here, which was capital M. M will be our 16 element array that's defined right here. So now we can say M at spot I, because that's 0 to 16, is equal to, and then we have to pull the first 4 bytes, or the j, starting at j, we need to pull every byte out of the block and reconstruct it into a 32-bit number. Okay, so what I did to cheat a little bit is it's not really cheating, okay. I went straight to the source of documentation, so I cheated by pulling up the documentation here. This is what I want. I've written this code a bunch of times where you get at spot j, then you logically OR it with j plus 1 shifted to the left by 8 bits, so you shift it over, and then j plus 2 shifted over 16, j plus 3 shifted over 24. This is what I want, so I'm just going to kind of copy this over, which is good because that way I'm just not shifting things to the right when I should be shifting to the left, yada, yada, yada. We should just be able to do this. So let me just look at that on the other screen. We should be able to do block at spot j, logically ORed with block at spot j plus 1, shifted over 8. Logically ORed with block at spot j plus 2, shifted over 16. Logically ORed with block at j plus 3, shifted over by 24. If this is broken, we're going to have a fun time debugging this. But it is going to be fun. You guys enjoy it. So yeah, this works. I think we can also just put this on its own line. I think that's it. I think that's valid. What we could do, I actually kind of want to go through and just see if we can implement it first, and then we can debug it. I think that's going to be easier. It's not normally the way I program, but I think that's going to be easier. All right, so now we have to initialize hash value for this chunk. This is easy because we're just making 4 variables here. All caps A, which is not global, whatever, is A0. That is whatever A0 is currently set to. It's initialized here, but it's going to be updated at the end of this function. So let's just do that. B, C, and D. So this will be, again, we'll keep these here. Not exactly how I comment code, but you know what? It'll make it really easy to find this on the Wikipedia implementation of it. So now we have to turn this into bash. So that's what we're going to do, line by line. For I in 0.63. We've been using the C-style loops. I think I'm just going to stick with that. For I equals 0, I less than 64, I plus plus. I like this better. Some may say it's like less bashy looking, but this is how I write bash. I write code like I'm a C programmer. We need F and G. So we need local F here and G here. And then we're going to check if I is between 0 and 15. So if I is less than 16, then we will do this. We will set F equal to B logically ended with C, or not B and D. Sure, whatever. Fine. We can do all that. That's not a problem. B and C, or not B and D. Believe it or not, this is valid. This will work. Oh, let me close the second parenthesis. No, I did that. Let me close the third parenthesis. There we go. Believe it or not, this is valid. This should work. And now G just has to be set to $I because that's what they've told us to do here. So now elif I is, we could say greater than equals 16 and less than 31. We don't need to do it because we're going in order. We should just be able to say I is less than 32 because when I is less than 16, it'll match this and it won't check the rest of the branches. Then when I is 32, we'll move on to the next branch. I think we can do this. We don't have to be so verbose here. So now we should have to copy this over. So this will be D and B or not D and C. Yeah, dude. Sure. Awesome. 5 times I plus 1 mod 16. Same deal here. 32 up to 47. So we can say elif I less than 48. I feel like that's just so much easier to read. All caps F will be equal to B XOR C XOR D. Now let's just keep the spaces here because I've been using them. G equals, sure. I don't know how much of this is going to stay in the video, guys. If I'm keeping this in the video, if I'm keeping all this in the video, then I must hate you guys. I don't know. I never know what to cut out because sometimes this stuff is useful to see. Times I. Okay. Now be wary of the below definitions of A, B, C, and D. Okay. So F now must equal F plus A plus K of I plus M of G. M of G must be a 32-bit block. So if you remember from the, I think it was the Wikipedia thing that said this, all variables are unsigned 32-bit and wrap modulo 232. We can wrap it. That's one way to do it. How I actually prefer is, I've done this before in previous videos, is I just make a mask. So let's go ahead and make a global variable here. U32 mask equals OX 1, 2, 3, 4, 5, 6, 7, 8. There we go. So this is all the bits turned on for a 32-bit number. We can logically AND numbers with this mask, and then we will get a 32-bit number. I'm more comfortable doing that. I just find that easier to do. Ooh, I scrolled all the way to the bottom. Big mistake. Let's see if we can implement this, because I think it's just going to be copying over exactly what we have. So this is F plus A plus K of I, which we can literally write this exactly like this. It's totally valid. Plus M of G, and then we have to run the whole thing through the U32 mask. And in order to do that, we have to put these in parentheses, just make sure we get the order of operations correct here. And that should be good. Now we just have to set A equal to D, D equal to C, C equal to B. See how if I get any of this wrong, it's going to be an absolute nightmare to debug. B equal to B. Okay, hold on. B equal to B plus left rotate of F by S of I. Trying to think of how I want to explain this. Okay, I've dealt with left rotate before. It's not that hard of a concept to understand. Is it here? I want to say I saw it here. Yeah, look at this. They even define it here. Rotate left where it takes 2 numbers. All it does is shift something, shift the input by n to the left that many, and then logically OR it with it shifted 32 bits to the right. This is, if you've done this kind of work before, it's very obvious what's happening here. If you haven't, it's very confusing. I actually kind of want to, I think I want to break this down in the video and show you guys what that means. So let's go ahead and not do that. Let's just put a to do left rotate. There we go. We'll just put that there. And then once we get to the bottom, this is actually pretty simple. We just set our global variables. We have global variables of A0, B0, C0, D0. We've updated these like local variables of all caps. We're just going to update the global variables. So md5 just keeps like a running tally every 64 bytes of data it encounters, and it just updates these variables. And at the end, that's what our md5 sum actually is. So let's go ahead and set this. A0 will equal to A0 plus A, but then be careful because it could overflow. So U32 mask, and then close that and make sure we get the order of operations right. There we go. And then we just do B, B, or no, C, D. This will be B, C, D. And this will be B, C, D. There we go. That is it. Believe it or not, that is it. We still have that left rotate thing to worry about, but this is the algorithm. I am looking over this code like you wouldn't believe because I don't believe this will just work. I just don't. I'm sorry. I know we still have more work to do, but like it's a lot of hand waving here, a lot of just copying implementation, hoping it works. Let's take a break from this. Let's do a little side tangent. I want to talk about shifting versus rotating. So let's make a script here. We're going to call rotate text. I was thinking about how to do this. We could do it with binary numbers, and we will do it with binary numbers eventually. But for now, I think showing text will be way easier to understand exactly what's going on here. Let's make our text say something like, hello world. Okay, simple enough. Let's get the length of that text. We can just say #text, and that's the length of that string. Now we can do a for I equals 0, I less than len, I plus plus, do, done. Let's go ahead and substring that text. So substring of text starting at I and going for the length of the string. We're not going to cut it off. We're just going to start at I. And then we're going to echo $s. There we go. I'll pull the source code back up so you guys can see it. Let's go ahead and run rotate text here. So don't be fooled. It's called rotate text. We're not actually rotating it. We're shifting the text. So this is probably very confusing to see, but we're just shifting it. See what happens when you shift it? 1 over, 1 over, 1 over. I'm going to show you what rotating looks like. Because if we just shift numbers, this is what's going to happen. But if we rotate text, we're going to get something slightly different. So instead, let's call this S0 and S1. And S1, instead of starting at I and going to the length of the string, let's start at 0 and go all the way up to I. So now we will print S0 and S1 right next to each other, okay? We won't put :WQ in the file. So here's the source code. Let's run this. And that's what rotating text looks like. It's very confusing if I just showed you that C implementation of it, even though it's one simple line. This, I hope, shows you a very simple way to understand what's going on here. And we're not going to be dealing with text, of course. We're going to be dealing with something like 001, 0111, 00000. We're going to be dealing with something like this. So if I show you what that looks like, you can kind of see what rotating it does. We shift it all left, but then we carry things forward. So that's what rotating is. I mean, since we're here, we kind of got to do this, right? Why don't we do something like hit that subscribe button? How's that? Run that. And that's kind of cool. You know what? We should put some spaces here. Hold on. Watch this, watch this, watch this. So if we put a bunch of spaces here, hit that subscribe button. Now here's what we're going to do. You ready for this? We're going to go into an infinite while loop. While true, do. We're going to put that in an infinite while loop. And then after we print it to the screen, we're going to sleep for 0.01. Wait, oh my God, even cooler. Hold on. Now I'm just having fun. Let's do a printf of a \r and a %. There we go. You ready for this? This is going to be huge. It's getting late, as you can tell. I'm getting delirious. But no, this is fun. So that's what's going to happen with the number. We're going to do that, but we have to implement that in Bash. So pull up md5 here. Let's go implement rotate. So we have this to do here that we left ourselves. We have rotate. We have this implementation over here. I plan on basically just stealing this implementation, but that's what it does. We shift it over by n, and then because we've shifted it over by n, we have to kind of shift it over the other direction by 32, because 4 bytes in a 32-bit number. 32 minus n, and then we put that on the other side. There's a lot of math here, but it's a very, very simple, elegant solution to this problem. So let's actually make a local variable here. We can make a local variable called rotated, and this will store the rotated value. So rotated, we'll have the math syntax, and then what do we actually have to rotate? What did I deleted the comment that actually explained it, didn't I? Left rotate f by s of I. Okay, so we have to rotate f by s of I. That's simple enough. Logically ORed with f shifted over by 32 minus s of I, and then make sure I close all of the right parentheses. Okay, that looks good. And then there should be no overflow here, right? I'm trying to think if this could actually overflow. Actually, no, it might. It might. Yeah, wait, this could overflow. So that means we have to put this whole thing in parentheses and then logically end it by the U32 mask. Okay, and then we have to actually go here. Let me just pull up this implementation detail real quick. B plus left rotate. Oh, okay. So it's just B plus the rotated value. And let me tell you, whenever you're doing a plus, you're going to run into the same issue. We're adding these two things together. We got to do the and with the U32 mask. There we go. Let's close that. I think this is it. I think that's all we need for the rotating. Okay, so what's left? We got to finalize the message, okay? We have taken the message in directly from the user, but we haven't done the other stuff that was on the page. If you remember, we need to, let me pull it back up so you guys can see it. We need to append the 0x80 and then pad with 0x0 bytes. We need to append the original length in bits. This is going to be super annoying. We have it in bytes so we could multiply it by 8, but then we run the risk of an overflow. We're going to have to figure out how to deal with that. Let's go down here. We have our main function, which calls process input. We have process input here, which calls process byte. So the only function we ever run is process byte from our input. That's really great. But process byte has the chance of firing off a process block function. Once that is all done, we might still have data in there. So now we have to, we've read the entire message. Now we have to finalize it by padding it and appending the length. So we're gonna have to do that. Let's go ahead. I'm just going to grab this stuff from the other screen, paste it in here like we did before. Whatever hotkey I just pressed, just close the terminal. How annoying, dude. All right, there we go. Let's close this, rerun this script. Dev bash md5. I'm gonna cut all this out, probably, right? And look at this. Oh, we have to recover the Vim file. And oh, we have everything still there. That's beautiful. Let's get rid of that swap file. That looks fine to me. Wow, we got lucky there. So let's not close Vim this time, and let's just append this crap in here. So it's called pre-processing here. We're actually post-processing it, but it really doesn't matter. So let's go ahead. Notice the two batting steps are implemented in a simple way. Pad it with 1 and then a bunch of zeros. So simple enough. According to this page, we just append 0x80. We do this no matter what. We append 0x80 no matter what. So we can just process byte 0x80. That just works. We're just giving it 0x80. We do that until the message length is 448, or in this case, 56 mod 64. This is really cool because it's actually really simple for us. We can do while the length of the block, remember that's an array that stores our 64 bytes of data, while the length of the block is not equal to 56, then we process byte 0. We add null bytes. Done. I wrote then, we want do. Now this is a little bit confusing, but that works. Because imagine the array is at let's say it's size 3. We just keep padding it with zeros until we hit 56. If it's above 56, let's say the array size is like 60. Well, we add a 61st byte, a 62nd, a 63rd, a 64. Once we get up to 64, and then it runs that function to actually go through all 64 bytes, and then we're back at 0, and then we just keep padding it with 0 up until we get to 56. Why 56? Well, think about it this way. We want to get to 64. That's the length of every... When everything's padded, we'll get to 64. We are 8 bytes away from 64, and the reason we're 8 bytes away is because we need to store the original length as a 64-bit integer. 64-bit integer is 8 bytes. That's why we're 8 bytes away. So we're padding it basically effectively. So we've padded it with our zeros and ones. Now we have to append the original length mod 264. It says mod 264. It's actually 2 raised to the 64 power. 64. It's a 64-bit integer. That's what it's saying. Now this is where I want to pull up the RFC because we have to see how to actually encode that data. I have an idea of how it's encoded. I just want to kind of verify that. A 64-bit representation of B, the length of the message before the padding bits were added, is appended to the result of the previous step. In the unlikely event that B is greater than 2, greater than 64, then only the low order 64 bits are used. So we can just kind of avoid those. We can just mask those out. These bits are appended as 2 32-bit words and appended low order word first in accordance with the previous conventions. So that's good. If I'm reading this correctly, I think it just means little endian. So this should be super simple. We just have to go through the low bits and then the high bits. We'll loop over them. It should be simple. I might, like I said, I'm bad at math, so I might overcomplicate this. It could probably be done in one loop. I'm going to be a lot more comfortable using 2 loops here. We'll see, because I've done this work before. I think for the BMP, I've done like a pure BMP generation, bitmap image generation in Bash. You can go check out that video. It's a super fun video, ton of fun. Another pure Bash video. But again, I'm just probably going to use 2 loops where I just do 32 bits. We'll see. Oh my God, yeah, no. Now that I think about it, I think we will have to use that. Okay, so it wants the length in bits. We have it in bytes. Now we could just multiply by 8. That'll probably work, but we do risk an overflow here. So it'll actually be easier, I think, to take that number, turn it into the high order bits and the low order bits. So turn it into 2 numbers that represent the bits, but that way we don't run any risk of overflowing. Okay, I think that's the safest way to do it, actually. So let's turn the byte length into 2 numbers, high bits and low bits. So local low bits and local high bits. I'm procrastinating because my brain is a little bit blank right here. Let me think. Okay, so we have bytes, we need bits. We can do byte count, shift it over 3. Might be a little bit confusing, but we're basically like multiplying it by 8. We're just moving it to the left 3. It's basically like multiplying by 8 because 2 to the 3 is 8. So we're converting bytes into bits. And because we've done this work, we should probably, this might be overkill, but it might be overkill, but it's safe. So I'm just being safe right now. And then for this, we kind of have to do the opposite. Byte count, we're going to shift it the other direction by 32. However, because we're doing bits, not bytes, we're going to shift it by 32 minus 3 because, again, the same 3 that's up here. And then this closes here, and then this also, just to be certain. Again, this might not be necessary, but I think we can just logically end it with the U32 mask. So we have the low bits and we have the high bits. So encode the full 64-bit int bits length as little endian. So we're going to loop over the low bits, then the high bits. For I equals 0, I think we've defined I up above as local. We have, okay, so we have I up above defined as local. I equals 0, I less than 4, because it's 2 32-bit numbers we have, so 4 bytes in a 32-bit number. I just keep reminding myself. I'm not talking down to you, to the audience. I'm talking to myself to remember how to do this, because this is the part that's stretching my brain the furthest. Let's just define that here. Local byte. Byte equals, we have to do some sort of math to extract the byte out of that part. Oh, this is easy. We've already done that to extract it before. Low bits, and to get a single byte out of it, we have to shift it over by I times 8, because I is going to be 0, 1, 2, or 3, and 8 bits in a byte. I times 8, and then logically AND it, not with the normal 32-bit mask, but with an 8-bit mask of 0xFF. I think that's right. I think that's how you get the byte out of it. Debug low bit at $I equals byte. Low bits at $I, that's good enough. And then when we're here, we can just, because that'll be a number, we can just add byte of byte because we're going to add it to the message. Okay. So then this just gets duplicated. Again, there's probably a cleaner way to do this, but this will be the high bits. This will be the high bits, and that's it. There's nothing else here, right? So when this is done, let's assume we did everything correctly. When this is done, we will have appended every single message. When we get down here, we should have, okay, so we were at 56 items in the block. Once we get down here, we should have 64 items in the block, which will trigger the whole processing of the block, which means the block should be empty. So let's just assert things are correct. Once we get down here, the whole block should be empty. So we should be able to check, like, if the length of the block array is not equal to 0, then echo, something went wrong. Write that to standard error, exit 1, FI. This is just a sanity check just to make sure we did everything right. So all that's left is to print the hash, which means we do have to format it. We'll have to figure out how to do that. But once we get down here, we just need to print the hash. That's super easy. So let's, like, we process the input down here. Let's just print hash. Simple enough. Let's go ahead and define that. Print hash. We'll just need to somehow print A0 plus B0 plus C0 plus D0. Remember, these are the global variables. So let's just debug this. We'll just say A0 equals A0, B0 equals... I don't think it's gonna be bad. I think these are just 32-bit numbers, so we can just go through and format them like Little Endian, I think, starting from the lowest one. We'll see. I kind of just want to test this. We've written a lot of code here. We should probably test it, right? Bash minus n md5. Okay, so it's syntactically sound. Shell check md5. It passes shell check. We could, let's cat files hello.txt. Let's pass this to a normal md5 program. That's what we should get. We're not going to get anything like that. Let's do debug equals 1, our md5 script. Okay, well, it's broken. All right. 0, 1, 2, 3, 4, 5, 6, not equal 56. Okay, so something is wrong here on line 141. And add byte command not found. Oh, did I call it add byte? Is it process byte? What do we call it? Add byte. I wrote that here. Process byte. I'm hallucinating functions. Okay. And line 141. There was something wrong. While not... Oh, I put an exclamation mark here, which loops the keys. We want this notation to get the length of the block. Okay, these aren't... For not having really tested this that much, that's not a ton of errors. Okay. Okay, it worked. Okay, HELLO, new line, then we pad it with OX80, and then we pad a bunch of zeros until we hit length 56, and then we set the low bit to 192.1. So 192 plus 256, am I reading that correctly? 192 plus 256. That's how many bits were in the original message, divided by 8 for how many bytes in the original message? 56? I don't think that's right. Oh, I know what's happening. Okay. This isn't good. Okay. Sorry, I don't know if it's clear what happened here. I looked at these, so I could see that we've encoded 192 and 1 here. So that's 192 ones and 1 256, because this is how it's encoded. So 192 plus 256 is 448 divided by 8. 56 bytes. We've encoded 56 bytes. That's not right. The original message is 6 bytes. So what's happening here is every time we increment byte count, where are we doing that? Yeah, we have byte count. We are keeping track of it every time we process a byte, even when it's bytes that we don't want to process. So let's do this instead. Where we increment byte count should only be when we're processing input here. So after we process a byte, we'll increment the byte count. After we do this, we'll increment the byte count, but we won't increment the byte count here and here. That makes sense. So this new number should be, how many bytes are in? Let's just see. It's a 6-byte file. So the new thing should be 6 times 8, because that's how many bits there are. Is it 48? 48. So it should be 48 embedded in there. That should be really easy to see. 48. There we go. And the rest are zeros. I think this is working. Like, am I crazy? I think this is right. Now, this doesn't look like an md5 checksum, obviously. We have to format it, but let's go ahead and do that. I don't think it's going to be that hard, because we've already taken a 32-bit word and formatted it as bytes. So let's just steal that logic and put it down here. And let's do that for each one of this. So we can do a for word in local word A0, B0, D0, do. There we go, okay. For each word in A0, B0, C0, Z0, we're gonna turn that 32-bit word into a number by extracting the single byte from it. So in this case, it'll be word. We're gonna pull out that single byte, and then we need to format that byte. So we're gonna printf hex, but we can do 0, 2, so it'll pad it with zeros of that byte. And then when we're down here, I think we'll just put a new line. This can't be. There's gotta be something. This is gonna break. Okay, hold on. It gave us B194. Was that right? Bro. Dude, there's no way. I thought there'd be more bugs than just that simple bits one. Okay, hold on. The empty string always comes out as that D41D. I know because almost if you put a V here, it would spell David, so that's why it sticks out to me. Wait, hold on, that's not our script. Hold on. Our script is md5. Bro, okay. Okay, now we have to test it on binary data, right? What was it? So if we run the built-in md5 on files random 4 kilobyte, we get this 94 whatever. If we run our md5 script on it, that's not even slow. That's fast. That's very fast. That's too fast to even benchmark effectively. We'll have to make a bigger file. Okay. Moment of truth, guys. Even though we already know it's going to work, let's run our test script. It works! Dude, it works. It works. MD5 in pure bash. And let's make sure it is shell check clear. That is beautiful. And it's actually kind of awesome. Like, it just works. That's crazy. Okay. Let's come up with some more tests, I guess. What was that word dictionary? User share dict words. It is, what is it? It's 4 bytes, right? Because it's a symlink. That's annoying. It is 2.4 megabytes. Is that going to take a long time? Let's see. MD5 user share dict words comes out to F920 whatever. Let's run our bash version of MD5 and let's time it and see how long it takes. Because, like I said, it's going to be slow. It's going to be slow. There's no way this works on any sort of timely feature. I probably should have ran it with the debug flag. I'd be kind of curious to see like what it's doing or how far along it is. Without statting the file first, we wouldn't be able to really make a meaningful progress bar. I could print how far along it is, but I'm very curious to see how long it takes to MD5 2.4 megabytes of data. I'm gonna let this run. I'm gonna go get a drink. So it's not fast. It's most certainly not fast. Never claimed it would be fast, but it is certainly not fast. What are some binary data we could do? I guess we could make our own binary file. Let me do a check real quick. What about bin bash? How big is that? 1.2 megabytes, so that should be a little bit faster. And it's binary data, so we can at least make sure that kind of works how we expect it to. If we do md5 bin bash, so it should be C223F. So let's do that. Let's do our version of md5 on bin bash, which is binary data. So it'll be twice as fast. What did that take? Like a minute something? So this should take like what, like 45 seconds roughly? So I'll cut the video. I forgot to time the command because I'm stupid, but that was roughly about 45 seconds. So yeah, it works. We have MD5 in pure bash. Just for fun, I kind of want to see debug equals 1 and just see like what it does. Okay, so yeah, dude, it is cranking away. That's so funny. Technically speaking, the more null bytes that are in a file, the more annoying it'll be because we have to call read more often. I wonder where like the actual bottleneck is. There may be ways to make this faster. Certainly getting the length of an array, I don't know how fast of an operation that is in Bash. We could probably store the length of the array separate from having to retrieve it. There are definitely ways we could clean this up and make it faster, but for now, like, it works, dude. Like, that's huge. That's awesome. We could add some sort of status bar. I'm not going to do that in this video. We can actually, you know what? Here, I will spoil a future video where I go over a tool I really like, because if you made it this far, you're a super fan. You're already subscribed. I don't even need to tell you to subscribe. You guys are awesome, yo. I appreciate you guys watching. There's a tool I really like called PV, stands for Pipe Viewer, and you can use it kind of like in line with your pipelines. So I can like echo high, pipe it to PV, pipe it to PV, pipe it to cat, pipe it to grep high, and it printed these 2 progress bars. You can see how fast a pipeline is moving. So what you can do is, instead of like cat bin bash and pipe it into md5, weird example, but you can totally do that. Instead of cat, you can just do PV. So it'll do the exact same thing, but PV knows how big it is, so it'll create a progress bar. Now, obviously, that ran really fast. But what you can do is you can PV bin bash, pipe it into our version of md5, and then run it, and this will give you a progress bar, which is super nice. So you can see, here's how fast the read end of md5 is consuming the write end of PV. So it'll tell you how fast it's going, how long it's been elapsed, how much data has been sent to it. Here's the progress bar, 38% done. We have an ETA of 28 seconds. So PV is amazing. It'll add a nice little progress bar. Now, PV is only measuring the progress of how much data has been read from it. So once md5, our program, has read all the data, it will say 100% complete. Our program can still do work. Obviously, it's not like a perfect progress bar. It has to append the message length and then calculate the actual thing that it prints the screen. Not much work. So once it's 100%, it should just be good. Should. There we go. Beautiful. Look at that. That's awesome. So again, run our test script and it works. That's amazing. There's not much more I need to do here. I think the only thing I would do is say like pure bash implementation of the md5 checksum algorithm. We could say like usage is md5 file.text or md5 file.bin, something like that. And then I'll just toss my standard header on it. There we go. And yeah, that's it. I don't think there's much else to clean up here. I think this all works. Just to make sure, shell check md5. Beautiful. Bash minus n md5. Obviously it's valid. And yeah, it works. I just keep running this to just keep like admiring my own work. Like this is crazy. Normally things don't work this well on the first try. I know there were some issues we had to clean up, but we cleaned those up and that's fine. So yeah, that's it. That's all I got for you guys. If you made it this far, you're awesome. Let me know what kind of content you want to see, what kind of content you want me to do. I know it's a long video. I know I can yap. I know I can make long videos. Let me know if you want me to make shorter videos. I've had people saying like, Dave, can you make more like 10 to 12 minute videos? Don't worry. I will always make deep dives like this, especially if you're at the end of the video. I know I'm selecting for the people that enjoy this type of content. So just let me know. Let me know what you think about this. Let me know if you enjoyed it. I'll put all the source code available online. And of course, I have to give a shout out to my Patreon or my patrons over at Patreon. I should just try that again. Let me give a shout out to my patrons over at Patreon. Thank you so much for your continued support. Look at Jordan's got color in their name. Karen, what an explosion. That's wild. I do like the explosion shows up for not a bard. That's pretty funny. Thank you everyone who supports the channel, dude. I think it's so cool. I think it's awesome that you guys are willing to give me money to get your name at the end of the video, and you don't even mind that dark space just completely takes over the page like that. That's so awesome. I do plan on doing a video where I talk about how to actually break the script and add fancier stuff to your name. I also want to make that accessible to people that don't want to modify their name, because I think it'd be cool if you all could like add your own little flair to your name or whatever, maybe as a comment or something. We'll figure it out. I don't know exactly what, but thank you so much for watching, guys. I appreciate it. Hopefully you guys enjoy this. And yeah, that's all I got. See ya.